Go ahead.
We are back. Good to see you. This is the review for the final for 351. You've made it this far. Congratulations. Hanging in there under very disruptive conditions here. Thank you for hanging in there and doing such a diligent job here with us, and we appreciate that. So this is for Wednesday, April 15th. Sorry about the compressed time. Our assigned day for the final is April 17th, Friday. So you'll be uploading that to Learning Suite. There'll be an answer sheet like on the last couple midterms. There'll be 70 problems normalized to 200 points. There's a lot of points yet to go between test 4 here and the final. That's 300 exam points. So the points being backloaded really rewards you for hanging in there and persevering and understanding all the concepts cumulatively. So yes, it is over all 15 chapters, 1 through 15. The homework book challenge, you don't need to turn that in, but you'll certify on the final. There'll be a checkbox. If you did it, if you honestly have solutions to all of the even problems at the ends of each chapter, you'll check that box at that time on Friday. So be using time this week to get that challenge book up to snuff and check that box. That's a great way to prepare to work the problems. Grading. Yes, we have to assign final grades soon. And I don't deal with that until, of course, we have all the final points in, and I plot them all out, and I look for that distribution. Yes, it is a curve, but it's a digital curve. It's not analog. So there are point breaks, and that's where I look to put the grade cutoffs. So I can't really say much about that, except that the grade cutoffs that are in Learning Suite right now are just approximate. So you'll have to trust me on that. Usually the curve is adjusted a little bit lower than that, but I look for the natural point breaks. I think that's a fair way to do final grading. I don't like hard and fast cutoffs. 90 and above's an A, 80 and above's a B. That's too artificial. I look for how you guys group together with your scores, and that at the end is how we'll do it. Check all your scores on Learning Suite. Let us know. Send me an email if there's something missing. You'll have to send me the original document, of course, and that's how I'll handle things. But make sure you get everything in there. Anything else on that? I think that's okay. We'll get the grading done, and there'll be a few days there where your grade will just appear on the Learning Suite website, and I won't submit it yet to the university. I'll wait for a few days to make sure that if there's anything else. So the next week is when you'll see your final grade showing up on the BYU website, but your final point total should be on Learning Suite. Make sure you double check all of those. So yes, very good. Today, of course, is the exam review. The final, sample final is on Learning Suite already. Hopefully you've been looking at that, 70 multiple choice problems. Most of them are single concept questions. Some are multiple concepts. Those are the trickier ones. Make sure you use your scratch paper and models as needed. All your best practices that have been applied to the midterms, of course, use here on the final. But 70 problems is quite a bit more there. And make sure you get it all entered and uploaded by that time. Okay, let's start out with some reaction problems. Reactions, remember, is the second level of understanding of organic chemistry. The first level is structure. The first few chapters were all about structure, Lewis dot structures, and the principles of polar covalent bonds due to electronegativity, hybridization, and resonance, and principles such as that we've been applying throughout the entire semester. But then the next step is reactivity, the conditions of starting materials and what goes to what. So we'll start out with combustion here and work these problems here. There's a two-step one down here, MCPBA first with that, and then LAH. Sorry, this is a little scrunched together. There's 3 reactions here on this alkene. See if you can do those. You want to pause and then come back. Okay, so combustion. Oxygen and a spark. Yes, alkanes, all organic compounds burn, right? And what are the two products here? Yeah, CO2 and water. And you can balance that equation as needed. If you have 4 carbons here and 10 hydrogens, C4H10, you can come up with the ratio of carbon dioxide to water. These are what? N-butane versus 2-methylpropane. Those are what type of isomers? Constitutional isomers or structural isomers. Which one will give off the most heat upon combustion? We can do that type of reaction. We've talked about that. If you have more branching, what? We say the molecule is more stable. It has a lower heat of formation. So upon combustion, it gives out what? Less heat. Less delta H here for the more branching. And we've seen that branching can lead to a change in the properties, right? Solubility and stability there. Let's see this reaction, alkenes. We did a lot of electrophilic addition reactions to alkenes. So hydrochlorination in this case would give us the Markovnikov product. Okay, the proton going out to the N carbon give us the secondary carbocation, right? And then the chloride attacking that addition reaction. And then we've got an alkene reaction here with what? Oh, that needs to be water, not hydrogenating with sulfuric acid. Yeah, make sure you double check the right combinations there. That can be important. So hydrogenating this, so protonate out on the end, secondary carbocation, and then we'll get a shift, right? So this product will look like this, the rearranged product. Now, if we hydroborate that directly, we'll also get what? Hydration of this alkene, but it will be the primary alcohol from hydroboration followed by treatment with base and peroxide. So no rearrangement there. Does not go through a carbocation. Well, what if we want this product here, which would be what? The Markovnikov addition here for hydration, but no rearrangement. Can we make that? Yes, this combination of reagents right here. First we form what? The epoxide here with MCPBA, and then what? Lithium aluminum hydride. We add the hydride at the end position, open up the epoxide, and look, we get the secondary alcohol, the Markovnikov alcohol. That's the only way to get it. You have to avoid a carbocation intermediate, which this does, hydroboration, to give the primary alcohol. So kind of combining the concepts, this goes back to what, chapter 10, and here we are further on, chapter 12 and chapter 11 there, and some other things that change the regio selectivity of that. There will be acid-base type questions on the final. You have to remember that. There's only a couple pKa's I told you have to memorize, and I think most of them you can figure things out there. So acetic acid plus hydroxide will just transfer the proton to form acetate and what? Water. Where's the sodium? Well, it's right there with the acetate. Will this reaction be favored to the right or to the left? Well, you can estimate it from the pKa's, right? Here's 5 pK here, pKa of 15. We're always referring to the acids in that case when we talk about pKa's. And we always go in the direction of what? The weaker acid, which is the higher pKa number. Remember, that's an inverse scale. So this Ka is 10 to the minus 15. This is 10 to the minus 5. So this has enough proton donation strength that hydroxide is a strong enough base to go ahead and form water. Right? How about this one? Here we have sodium ethyl amide. The sodium salt here. So keep track of what's on there. That's sodium cation and nitrogen anion. You don't always draw out all the charges and Lewis dot structures. And then what do we have reacting here with phenol? So what's going to go on here? What's the acid and what's the base? You could say, well, there's still a hydrogen here. Maybe that's the acid. Well, there's a hydrogen here. Maybe that's the acid. So what would you pick here? Well, that's a strong base, right? This amide anion here. It's going to go to the amine, ethylamine, and then what? The phenol ends up as phenoxide, O minus. Again, the sodium's associated with that. So how do you figure this one out? Well, if you know the pK of an alcohol, and this one's a little bit more acidic alcohol because of the resonance, That pK is 10. Maybe you remember that one. And then the amine here is 38. Okay. So which direction are we going in here? Yeah, certainly to the right here for that one. Let me come up with one maybe where it's not favored there. How about this one? How about if we had phenol and water going to protonated phenol and hydroxide? If we drew a reaction like that, could you tell what's favored here? Let's see. So here would be phenol grabbing a proton off there. And if this is our acid, then I know what that's 15. And then protonated alcohols, what those are -2 or so. That's like hydronium ion, right? Protonated water. So there your acid is hydronium ion of a phenol here versus water. So what direction are we going in here? Well, we're going toward what? The highest number here, or the weakest acid. This is a much stronger acid. That's going to easily donate a proton to hydroxide, which is a good base, right? Going back to water and back to that. So the equilibrium here would be far to the left side in that case. All right, yeah, there's many you can come up with there. Keep straight pK values. And if you know those two, you should be able to figure a lot of things out. Water's, of course, a good one to know there. Let's see, what reactions are these? So we've got a secondary chiral chloride, that is what? The S form there. And we've got a charged small nucleophile. So what type of reaction is that, right? SN2, so we get inversion of the stereochemistry and form the azide there, the R product there. Secondary is kind of on the borderline, right? They're slower SN2 reactions. Primary would be faster here. Because what? That backside attack with a charged nucleophile, backside attack would go faster if this was primary. Of course, there wouldn't be any stereochemistry involved there, but secondary here can participate in all types of reactions, which you see here. What about sodium Tbutoxide with a secondary? That's right, E2, elimination. Always do elimination E2, unless it's a methyl leaving group. That's the only one you can do SN2 in. But even if it's primary, it will do elimination. Okay, Tbutoxide. Why? Because it's charged, strong base, and it's highly hindered, so it's a weaker nucleophile, so the basicity factor takes over there. And what about this? Methanol is a neutral nucleophile. And what type of reaction we do here? We're not going to do bimolecular reactions with a neutral nucleophile. It's not a strong enough nucleophile now, being neutral, right? If this was methoxide, O minus, we'd expect what? SN2 again. And that's small enough to do SN2, whereas Tbutoxide does all E2. But with methanol, what type of reaction are we doing? Yeah, SN1 now. Yeah, so let's get all these up here. SN2. E2, these are the important ones. SN1 is going to what? Wait around for the ionization. Secondary carbocations, okay, it's not great. Tertiary one would be faster, but it's secondary okay. And then attack, loss of the proton, we get the methyl ether. Okay. But what about the stereochemistry? Oh, because it goes through a flat sp2 hybridized carbocation, right? That's trigonal planar. Attack from the top or the bottom. Gives a mixture of enantiomers there. That is a stereocenter. So this is a nice one here to review those principles from that earlier chapter. All right, let me get some others up here. And we'll give you another chance to pause and go through them. And then we'll go to the sample final and click through every problem there and see what you'd like to go over there. Here we got an alkene. We're going to brominate it. Bromination with water, osmium tetroxide on the same thing. And let's see, how about HBr with the same thing? And then how about HBr, but in the presence of peroxide? Yeah, there's a good review on that one. How about with that same substrate, treat with ozone, and how about an alkyne reaction? Two equivalents of HBr. Let's see, I do have a couple more. How about that same alkene, but with NBS and light? So this is going to chapter 15, so we're coming up to all of them here. How about an alkane reaction with bromine, Br2, and light? So do those there. Pause if you need to. And we're back. So what do you have here? Well, we have bromination. And when it brominates here on the cyclic one, you can see the anti-relationship between the 1,2 bromo groups. And that is a mixture of enantiomers. These are both stereocenters. Your other enantiomer would have these two stereocenters just inverted, so you'd stay together all there. Okay, if we do the bromohydrin, bromine with water, we'll have the same bromonium ion, but what? We'll have water now attack, and water attacks anti, and loss of the proton that gives the bromohydrin, where the water attacks at the more substitute carbon. So put the bromide at the less substitute carbon. Bromide is the electrophile in this case, so it goes out on the end there. Osmium tetroxide also gives a chiral product. It gives the diol in this case. And that again is a mixture of enantiomers. Both of these, well, all three of these would be features there. But where these two are what? Anti the electrophile moving cloud. Here, osmium tetroxide just reacts in a syn manner with the same phase, so the osmate is broken up to give you the cis diol product. Okay, what about this? HBr. Does this one give a chiral product? No. It's a chiral product. That's regular Markovnikov, what? Hydrobromination, where the electrophile and the bromide ion on the end, and the tertiary carbocation is formed there. And then in chapter 15, remember we have HBr hydrobromination, but under radical conditions. So again, this will give us a mixture of products. And this actually gives a mixture of the cis and the trans products. Both of them are chiral, so I think it's 4 different products. You can draw them all. But the regioselectivity is the key thing, being complementary to this conditions without peroxide. With the peroxide, the radical pathway goes there. You can say these are similar mechanisms, right? You've got the electrophile, in this case, the proton off the strong acid goes to the end carbon. Whereas here, what's the electrophile? It's not the acid here, it's initiated with the peroxide. So the electrophile is actually bromine radical, which adds on the end to give you the tertiary radical in this case. And then the next propagation step, that carbon radical grabs a hydrogen atom off more reagent, more HBr. So looking at the mechanisms of these two, they're very different. Why? Because of the radical conditions. So these type of questions are favorites for these type of tests. Make sure you can understand these complementary type conditions within that. Okay, what about this one here? What do we mean the same one here? I think we're referring to the alkene up there. So if we do molecular scissors here, we'll get the aldehyde ketone, right? So that bond right there, in the 5-membered ring, you just break both the sigma and the pi bond. You put in oxygens with osmium, you get out the ketone in that case, and then the aldehyde there. Okay. If we react an alkyne with 2 equivalents HBr, what do we get? We get out a double, what? Markovnikov hydrobromination in that case, where the proton always goes on the end, and then the cation gets trapped there. All right, what about this one? NBS with an alkene. Well, we'll go through the radical, right? So there's one intermediate, right? And the radical can either be here or here, but there are a couple different ones. Let's start drawing products here to see what we'll get. We'll get that al bromide, plus we'll get bromination on the other side. And is that the only one? Well, that's taking a hydrogen atom off there. What if we take the hydrogen atom off there? We can then get what? We can get bromine there and the alkene moved over. And that's not the only one, right? We can also get the bromide down here and the alkene back in its spot there. And is that the only one? No, there's also this allylic hydrogen over here, which would give us this one. So yeah, I think we did this one, the chapter 15 one, or was it the exam review for test 4? Maybe we did this one. I think there's at least 5 there. And some are chiral, right? This one's chiral, this one's chiral, so's that one, and that one. This one's achiral. This is not a stereocenter here, but all these others you can draw as DL pairs. So that's the tricky one. What about bromination of an alkane? Remember, that's a reaction also in 15. And remember, bromine is highly selective. So under light conditions, room temperature, with an alkane, look for the most substituted carbon position. That would be right there, right? So our only product in this case for bromine is that one. Now, if this was chlorination, we'd get chloride here, as well as here, 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 and here. We'd get a lot more products, because chlorine is not selective. Both steps of the propagation are exothermic, okay? Whereas bromine propagation steps are endothermic, so we can differentiate easily between the transition states at the more substance spot. It's over 1,000 times more selective for a tertiary position over a primary. So those are some there. Let's add some more up here. Yeah, a lot of reactions to review. This is a great way to review the topics. How about if we have vinyl chloride and peroxide? What's the product? How about if we have an alcohol here and we treat it with sulfuric acid and heat? How about if we treat that same thing with sodium hydride and then methyl iodide? How about if we treat that alcohol with chromic acid or PCC? Okay. Or what if we take it and treat it first with tosyl chloride and pyridine, and then treat it with ammonia? What are we going to get? Let's treat that same tosylate here. Sorry, I'm adding that on there. And let's treat that with lithium acetylene, and then let's treat that with palladium linolol and hydrogen. Got to include that. And let's take that same intermediate, whatever it is here, and treat with water and sulfuric acid. So again, we're getting an intermediate here. Or we can treat it with borane and hydroxide, peroxide. Or we can take this intermediate here and treat that with borane, BH3, hydroxide, peroxide. Okay, there's a bunch more problems to try. See if we can handle all of them. Okay, and we're back. What do we get here? We take an alkene, and we don't have any other reagent except the peroxide initiator. Well, we're going to get a polymer. Okay, let's just draw a couple units here. So each 2 carbons here in the polymer, X, hundreds or thousands of carbons long there. Every other carbon is going to have whatever is on the alkene. So the chloride goes along for the ride. And what are we going to call this? If this is vinyl chloride, this is what? PVC. There are a couple other simple alkene polymers to keep straight. So we can ask you about what's the monomer if we give you a polymer, or if we give you a monomer and the conditions here, what is the polymer that's formed? That's another way to do it. Okay, back to previous chapters here, combining different reactions in some cases. Sulfuric acid, heat with an alcohol. What do we get? We get the alkene, correct? Okay. So that's what dehydration reaction. It's just the reverse. If we treated the alkene with strong acid and water, that'd be different conditions. We'd go to the alcohol. But there's no water involved here. It's just the strong acid and heat. And that way we'll what? Pull water off this and favor at equilibrium the alkene product. If we treat with sodium hydride, what do we do here? That's right, take off the proton, form O minus. And O minus is a good nucleophile now. And there's a leaving group, methyl iodide, being a very good SN2 leaving group, will give us what? The methyl ether product. Yeah. And we can do what to it with chromic acid here, H2CrO4. And that's a common mistake here. Make sure you see the chromium there in that region, where this was sulfur. This is not an oxidizing agent. That's just to help protonate the alcohol and then eliminate water. This forms a chromate ester and then does the oxidation, because chromium is a redox active transition metal, right? It can undergo reduction. And when it does that, it will do it a couple times. It will fully oxidize the primary alcohol onto carboxylic acid, correct? Remember, so PCC, pyridinium chlorochromate, will stop at the aldehyde. So important to keep those reactions straight. A couple of these are from previous chapters. These two, I think, are from chapter, what, 12? The oxidation reduction chapter. This one too, tosyl chloride, turning the alcohol into a tosylate, and then displacing the tosylate leaving group with what? Ammonia, which is a good nucleophile. Even though it's not charged. A couple steps there in the mechanism. We have to do the attack with the lone pair on ammonia, the neutral amine, right? And then there's originally, what, 3 hydrogens on it? It would be an ammonium cation, and then you use another equivalent ammonia to deprotonate the ammonium cation there. But you can form the methylamine there from that. Let's see. Primary tosylate, that's the same intermediate we're talking about. What's our leaving group here? Well, it's that whole tosyl group. Make sure you remember what a tosyl group is. And then we form the alkyne. And count carbons here. 1, 2, 3, 4, 5 total carbons. You bring in 2 at a time on that, unless there's something else here, right? So there could be another group there. But this is a good one to compare here. So if you have an alkyne with Lindlar's catalyst hydrogen, yep, you stop at the alkene. Now there you don't see the cis-alkene. You can partially hydrogenate terminal alkynes and stop at the alkene. And that's useful, right? We went from a 3-carbon alcohol to the end. Now we have the 5-carbon alkene, okay? And that's synthetically a useful thing. Let's take this same terminal alkyne and do what? Here we're hydrating it, and we're going to hydrate in a Markovnikov way to give the alcohol right here. That's a vinyl alcohol or enol intermediate, which will what? Tautomerize, right? To what? The ketone product in this case. So the final product will be that ketone. From the protonation out on the end, alcohol formation here, and then tautomerization of the enol to the ketone form, which is more stable. Let's get these products up here. Oh, but if we hydroborate the terminal alkyne, we'll put the electrophile on the end here, which is boron. That'll form a vinyl alcohol in a different spot and give us what? The aldehyde carbonyl product, okay? So these synthesis problems kind of help you review some of the selectivity issues from that chapter. I think that was chapter 10 also. No, with the alkynes it was 11, right? Okay, keep track of that, yeah. And let's see, if we hydroborate the alkene and do the workup, we can get yet another product, right? We can get the primary alcohol. So there we went from originally a 3-carbon primary alcohol to now the 5-carbon primary alcohol. You can see combining those steps. Anyway, some very good applications there. And I think that's all the problems I wanted to do that way. Just to point out to you some formulas. Let's go to the overhead here, Isaac. And at first we'll kind of click through some of the review materials. And I do have a lot of review materials on Learning Suite. They've been there the whole semester. They're under the content, I think, handout materials. And these are CHEM351 reaction reviews, okay? But click through all those documents. There's a number of things to look at there. So here we have a bunch of reactions. Let me go to the first page in this. And this is the stereoisomeric relationship between different compounds. So what type of isomers do we have? We've mentioned a couple already in this review. We have what? Constitutional isomers, which have different bond connectivity, right? Straight chain or branching is an example of that. And then we also have what type of isomers? We have conformational isomers, where rotations around sigma bonds can give us the gauche versus the anti-butane, and the chair flipping of cyclohexane, exchanging equatorial and axial positions. Those are all conformational isomers, where we're just rotating around bonds. And those are very low energy interconversions, right? Those are in equilibrium. Constitutional isomers are not in equilibrium. So are stereoisomers, okay? These are the same connectivity, same type of constitutional arrangements, but different types of array in three-dimensional space. So, you know, we've got conformational isomers, rotation around sigma bonds. We've got constitutional or structural isomers, are identical, you know, if you're just looking at a different orientation. So these are examples of all these, to review those. The tougher ones are what? Enantiomers and diastereomers. Enantiomers are what? Stereoisomers that are non-superimposable mirror images. They're like the left and the right hand of each other. And that's where all the stereocenters are inverted. Remember what a stereocenter is. That's a carbon sp3 hybridized with 4 different groups on it. So here you have an example of just one stereocenter. Here's ones with 2. And I think there's 3 here in this example, looking at these Newman projections. Yes, you can bring models, of course, on the final. The trickier concepts, make sure you go through that and review that. Diastereomers are stereoisomers, same connectivity and everything, but what? They're not mirror images of each other. What that means in practice is they'll have 1 or 2 stereocenters in common, but at least 1 or more are different. If all the stereocenters are different, those are enantiomers of each other. If there's just one stereocenter change, then they become diastereomers. Okay, so different concept there. Then we have the relationship on rings. We talked about cis and trans relationships there. And on alkenes, we talked about cis and trans relationship. Remember, if you have 3 or more groups on an alkene, you should really talk about E and Z isomers to be more precise there. So yeah, a lot of flavors of isomers, but that's in the structural area. The first concept of OChem is to keep those straight. Then we got all the reactions. We've already been doing a bunch of these, but the graphics on Learning Suite, you can look at these and help yourself review. I'll have to warn you, we haven't covered some of these reactions. I think most of them though, yeah, okay. Just looking at those, I think we've done all those. Secondary with the stereocenter, that's where we got that stuff going on. Tertiary and secondary, that's where we have SN1 with the neutral nucleophiles, okay. If we have a charged nucleophile tertiary, you know, then we're getting E2 mainly. Then we got the tosylates here, and then we got the other conversions with alcohols, right? Don't forget about socyl and PBr3. There we go to that. And what's the other elimination thing here with alcohol? We had phosphorus oxychloride, right? POCL, which also does the elimination directly out of alcohol. That would be over here for this with, not with a tosylate. Where is it? Yeah, it's not up here, sorry. Okay. Yeah, and then TB toxide, yeah, and others there. Okay. So it's a good way to review along with working the problems. And remember, I had this decision chart. Also, I showed you this in class. You know, come up with other examples for this to help you keep this straight and what's going on there. You know, if you have a charged molecule, generally think about it being a stronger nucleophile, okay, and you know, primary and methyl are going to be the fast ones. Bimolecular attack's not hindered, so you can look at that. Tertiary, even with you know, a charged guy, we did see SN1 for that tertiary. That's one we did early on. So it's examples where, you know, there are exceptions to the general rule there. But TB toxide, yeah, always elimination here, except with methyl. There's the only one doing SN2. And then we have the stronger bases here that are smaller, yeah, mainly SN2. Some E2, depending on how they're set up, if you have the leaving group and the proton fixed, rigid, anti to each other, you'll generally begin to favor more E2. And those are shown mainly in the cyclic structures that we saw, where they're codiaxial, where we see mainly E2. Tertiary, always E2. It can't do the backside attack on tertiary. So the only thing that's left to do here with a strong base is E2. And then here we have the weak bases, neutral here, SN1, or no reaction if it's primary, or just a solvent here, no nucleophilic character at all, no reaction or even. So, focus on the archetypical examples there. Those are the ones you need to be concerned with. Don't get hung up in the gray areas there. If it is kind of a borderline thing, we'll give you some other information there. This interconversion between alcohols and halides, very important one. There's our sockle again. We can also interconvert with HCl or HBr, right? Or we can do an SN2 reaction if it's primary, secondary, to go from the halide to the alcohol. And then all these other reactions. I don't think we didn't do the ether reaction for this class. We did the PCC oxidation and the chromic acid one there. And certainly no, we haven't done the organometallics there. We did over-alkylation there. There are ways to shut that down. If you use excess of ammonia, you'll get the monoamine. If you have excess of the chloride, you'll oftentimes get over-alkylation there. And then, yeah, we did that one and that reaction. I think we're fine there. Oh, we haven't done the esterification. That's 352. We haven't done all the alcohol reactions yet, so. And then all the electrophilic alkene additions, the 5 H's, there they are, I think. 1, 2, 3, 4, 5, yeah. Halohydrin. Some of these we haven't done. We didn't do cyclopropionation. That's a 352 reaction. We did that one, did osmium, ozone, epoxidation. Any peracid will actually do this. MCPBA is just one of them. And then the special cases with the rearrangements are important there. And then if you have a cyclic alkene, there's stereochemistry issues for some of these reactions. And then the epoxide reactions. Maybe it's good to take a little time here to review these. Form the epoxide. The epoxide's always cis stereochemistry. You can open it up with LAH at the less hindered spot and get the alcohol. Don't worry about this magnesium reagent yet. That's a Grignard reagent, 352. You can open it up with hydroxide, again at that position there, and you get the anti-relationship in the diol. Or under acidic conditions here, right? If you have sulfuric acid and methanol, you'll protonate the epoxide, open up, get the flat tertiary carbocation, and then this can come in top or bottom. Usually they're anti to each other is the major one. That's probably what we've been showing, which is a combination of sterics and opening at the more electron deficient spot, which will be the tertiary position there. Same thing with that. This opening here under more basic conditions, SO2 type, will give clean anti-selectivity. This one under acidic conditions, again, you get a lot of carbocation and your stereochemistry will be eroded there. Okay? So some reactions to keep straight there. And let's see, alkyne reactions, yeah. Got a few of those. We've already been reviewing these, I think. Yeah, the hydroboration thing. I think it's important. The hydration gives the ketone versus aldehyde there. And hydrogenation with a normal catalyst gives alkane. And then we've got the Lindlar reduction cis, and yeah, the sodium ammonium transalkene. Okay, yeah, that's a great way to review, focusing on the reactions. We had 4 new reactions in chapter 15 was this, right? Alkane, this is the only other reaction with alkanes besides combustion. We've got chlorination, which is not selective, 4 different products in this case, whereas bromination is mainly or exclusively this tertiary bromide in that case. Then we got, allylic bromination with low concentration bromine and light or heat, or NBS, which is better. Much better. It's not corrosive, solid material. It's a lot easier to deal with. And then light or heat. We'll do both there, allylic bromination. Then we've got hydrobromination, which is the complement of just regular HBr. This is now in the presence of peroxide, giving us the anti-mercaptan product. And you may want to compare these two reactions at this point. There's always a couple students who ask me about the mechanistic comparison there. These both involve alkenes, right? And they both involve bromine radical. How come you get two different products here? Wouldn't you just get the same product at least? What's different about this? Well, notice the second one is from HBr, okay? There's a proton, a hydrogen atom that can be abstracted first by the oxygen radical, giving the bromine dot. This generates bromine dot though here, okay? So you could say, well, instead of forming allylic bromination, how about in this one? How come you're not forming allylic radical here? Well, you are actually, but that's reversible. Now you have a hydrogen atom source. You don't have that here. You just have bromine radical and then, or NBS that can chain carrier it here. Your byproduct is HBr, actually, in this case. But at the initial phase of this reaction, it's all allylic radical. You don't have the HBr present, and this will just propagate in such a way to give the albromine. Whereas here, as soon as the bromine can add to the alkene, then you have a hydrogen atom that can just transfer to the substituted carbon radical position, and then you're done. You've got the closed shell product there. So these are different mechanisms. They're very different if you look at the reagents and the details of the steps there. And then if you leave out the reagents here and just have the initiation of an alkene, you get the different polymers. And you should know, these abbreviations, what they mean, I think. But structurally, that's the important part there. Okay, I think that's for it for the review there on that. Let's go there. I've got the answers there, and we'll click through, and I'll point out the best I can, the ones that I think are maybe a little trickier, or just give you a little more insight there. And the level of difficulty in the coverage, I think, here is very indicative of how typically we have a final. Normally we use the ACS final, but this is one where it's put together of a number of multiple choice questions. It was a final in the old days, but it's very indicative of the level of understanding and the coverage here. A lot of these ones early on are structural issues. There's some naming problems, but again, we get into reactivity heavily, spectroscopy, and some mechanistic discussion there. So yeah, don't forget about Lewis dots and formal charges there, empirical formulas there. And we told you there's more information in these empirical formulas. You can see what 1 degree of unsaturation here with the 1 ring. This one is, and there you just count up your hydrogens and carbons. So, early on in this course, that was an important skill to have, especially with these skeletal stick figures. Every carbon in a corner, and then add in all the hydrogens there to get to H20 there. Know structurally what a double bond is. An alkene is what? A combination of a sigma bond and a pi bond between two carbons. There's 4 total electrons there, sp2 hybridized. Why? Because the pi electron's made up of a p atomic orbital overlapping sideways, right? Correct name here. This is kind of a tricky problem here. You can count down here and form a heptane a couple different ways. Why is the heptane along here, and you name this as an ethyl group? You could name along here and call this what, an isopropyl, and this is part of the main chain. There's another rule there to keep straight, and that's what? Minimize branching, if you have a choice there. You always maximize the longest possible parent hydrocarbon, and that's heptane in both cases. But if you go down this way here, you have a methyl and an ethyl group, okay? And there you're maximizing branching instead of using this branched prefix name as an isopropyl. That's just part of the rules there, so it's C there. Isomers of C6H14, primary are methyl groups, CH3s. Secondaries are methylenes, CH2s. Tertiaries are what? Methynes, CH1s. And the only one here that's just primary, CH3s, methyls, and CHs, methynes, is this one, 2,3-dimethylbutane. And that's important, so just go down here quickly, Isaac. So a problem like that, number 5 there, draw out the possibilities, right? And if you draw them out, you know, maybe your brain will start to kick in. There's a connection between your hand and your brain. And that one, you know, you're kind of testing your nomenclature too. We're not just showing you the explicit structures, we're asking you based on their names. So yeah, spend some time and draw them out. Don't just latch on to the first problem, the first answer that seems to make sense. You draw this out and you see what the 4 methyls and the 2 methynes for that one. And yeah, you can go back up there. Sorry, we'll have a little back and forth there. And then this one, dipole moments. So these polar covalent bonds, you know, there's 4 in this one. Why isn't that the most polar compound? And here we're asking about the compound with the largest dipole moment. So it's the molecular dipole moment. Here they're all pulling in opposite directions, right? In the tetrahedron on tetrafluoromethane. So that is a dipole moment of 0. These here, conformation, these are canceling out here. If these are diaxial or diequatorial, 1/4 of each other, these polar covalent bonds are pulling in opposite direction. These two are enforcing here if they're 1,2 on a rigid benzene. So this is your one with the highest dipole molecular moment for the compound there. And you know, read it carefully there, you know, to get what's being asked there. Here's something on properties, the order of increasing boiling point. So you pick the one with the lowest boiling point first. You're putting them in order here with these Roman numerals. So the branched hydrocarbon one here would have the lowest boiling point. In fact, it's probably a gas at room temperature. I think its boiling point is like 10 degrees Celsius. And then this one's a little bit higher, being straight chain. So yeah, 2 to 3. So the alcohols, because of hydrogen bonding, those have much higher boiling points. And which one would be highest? Well, the primary one. There you can get the multiple ones closer together, being at a less hindered spot. Tertiary, secondary spots are more hindered to do your hydrogen bonding. So your highest boiling one here is the Roman numeral 1 there, which is what? Lowest to highest, so D is the answer there. That one's a little tricky. You gotta look through all the structures and think about what's being asked about boiling point, which is a function of strongest intermolecular forces, right? Weakest to highest. Naming combined with RNS, yeah, I think you can go through that. Okay, alcohols on the straight chain there always have the lowest possible number. It's 1 in this case, and that's a phenyl group. Benzene is a prefix name, it's a phenyl group, which might be confusing there for that one. Acids. So what's your weakest acid? Which is what? Has the highest pKa. Which one is least likely to donate a proton? Well, these hydrogens are all on heteroatoms. Which one's different here? Well, the alkane, right? The pKa of a CH alkane is about 55, which means the Ka is 10 to the minus 55, right? You could put these in order, right? This would be 55, this one would be next at about 18, this one would be next at 10, and this one would be at 5. So we can order these too. And from those couple that you have memorized, you can look at the structures and figure those out, okay. This one here, we're monochlorinating. How many total products? Well, 1. All 4 of these methyls are the same by symmetry, so there's 1 primary there, 1 at the methine, and that's the same over here too, and then 1 there at the methylene. And then you have, because of the symmetry, how many total constitutional isomers here? 3. Okay. E2 reaction, most likely to occur tertiary, yep, and a hindered strong base, TP toxide. Okay, that's going to make E2 the only pathway there. Alkene react fastest with Br2. So in this case, the alkene's what? When we talk about the mechanism of alkene reactions, electrophilic conditions, the alkene is a nucleophile. What's going to make that nucleophile react faster? That's right, if it's more substituted, more electron rich. So the tetrasubstituted alkene reacts at a much faster rate than these other lesser. The slowest one would be the monosubstitute alkene. So we didn't talk a lot about kinetics, but you can think about it from a mechanistic point of view and get that one. Ozonolysis. So which one here? Again, combining the nomenclature and then these products. Maybe we'll come down to the board here on this one, Isaac, and think about this one. Here it's another good idea to break out the scratch paper and figure out what you got to do there. So here we got one product, right? And we got this ketone aldehyde here, and then we've got another ketone here. Okay? Notice this has the 2 carbonyls here. So if we stitch those 2 together, and then these 2 together, one of the compounds on that list there, and the nomenclature, is a little bit tricky there, but we'll go back up to it in a second. Here you can see it if you come up with the nomenclature and draw out the structures for the 4 answers there. This one, you see the products. Here's the acetaldehyde, this 2-carbon unit. Once you break that, a double bond, and then right here you got the methyl ketone, and then aldehyde right there, right? There's a hydrogen there. There's methyl there. Then you got this methylene and the methyl there, and the methine, yeah. And then the ketone there on the 4-carbon ketone. If you go back up to the nomenclature, you can see that that is that nonadiene, 3,4,7-trimethyl 2,6-nonadiene. If you draw out all the other structures and then do the ozonolysis, this one takes more time. You need to invest a little time with scratch paper to do this, because the combination, you could say, of what? Nomenclature and the reactivity of the ozone. But if you go through it sequentially, you should come up with the correct answer there. All right, let's see, what else have we got? Oh, stereoisomer problems. How many total isomers? Stereoisomers, again, they're all the same constitutional isomer, but in 3D space, this is a consequence of what? The number of stereocenters to the power of how many you have there. So what have we got? We've got 5 stereocenters, they're all circled right there. So 2, those are the 2 possibilities, RS, up or down, right? So it's a total of 32 isomers for that compound. So that's where the complexity of organic chemistry comes in, I think. A lot of possible isomeric products there from that. If they're all inverted, those would be enantiomers of each other. If it's just one or not all of them inverted, those are diastereomers of each other, right? Then we got what? Fastest by SN2. So asking more details about the mechanism of SN2. What does that mean? Substitution nucleophilic bimolecular. So what nucleophile can hit the back of these carbons more efficiently? Well, the primary ones, A and C, I'd say. What's the difference between A and C? Well, there's a methyl here next door to that backside, so it's got to come in past an isopropyl group, really, to hit the back of that carbon. Whereas here, it's just got to come past this ethyl group. So no branching here, this primary one would react faster. And I had some actual kinetic data when we did this chapter, and you can refer back to that, but certainly secondary and tertiary would be very slow for the probability of a charged nucleophile to hit the back of those carbons. And that's approaching what? The sigma star of those molecular orbitals. 16 is always a tricky one. Students always ask a lot about that, how to approach that, because you can kind of see here, looks like that stereocenter. Once we, and what kind of nucleophile is this? This is the sodium salt of sulfur, what? Dianion, okay? And that is a known nucleophile. It reacts once, and then it's still a charged nucleophile, okay? So the 2 negative charges go away sequentially there. And we have, what, 2 leaving groups in this molecule. You do this under high dilution conditions to get a good yield of the cyclic sulfide product. You can get a decent yield if you do it high dilution. You don't need to worry about that. They're all cyclic products. We're testing you on the stereochemistry here. These are the SS, chiral one here. It's not meso. Okay, could ask you about the meso here. But this is the SS, so if you do the backside attack here, and then backside attack there, you invert both of those centers and assign R and S to all the stereocenters. You see, this is the only one that inverts from SS to RR. This one looks a little tricky there. That looks like we retained the stereochemistry. Nope, we got a different orientation. This is puckered up, and this is puckered down there on our chain. So, but if you assign R and S, you can keep that straight. So that's kind of the key for that one. And always, if you do an SN2 on the secondary, make sure you're thinking about R and S there, okay? So C is the answer there. How many different sets of protons does this compound have? I assume this is referring to proton NMR. I didn't state it, but yeah, I could have been more clear on that one. So how many signals would you expect to see in the proton NMR? That may be more accurate. You got this ethyl, those are two different sets there. You got the alkene, that's a third. And what about these two methyls here? Again, this is a rigid alkene, right? So this one is what, cis-arrayed to the carbonyl there. This one over here is trans-arrayed. These are different methyl groups, different magnetic environments, so they're going to have different shifts. So how many? 1, 2, 3, 4, 5. 5, yeah. This one, SN1, let's see, a vinyl bromide? No, we don't do substitution there. SP3, yep, secondary. SP3 secondary, oh, and primary. SN1, well, you might be able to rule out the primary here, but check a couple things here. What if SN1, we're with a neutral nucleophile, the slow step's ionization. So if we lose bromide anion here, we have an allyl cation, resonance stabilized. That's going to be quick. How about this one? Is this an allyl bromide? No, that'll be a localized secondary cation. Same thing here, localized primary. So this will be the fast one. Okay, so analyze that, see how stable that cation is going to be. Resonance structures will make it more stable. Multi-step synthesis one, I think that's pretty straightforward. We've talked about a couple of those. Same thing here maybe, although this reagent's a little bit different. This is hydroazidic acid. We're under acidic conditions. So we protonate the epoxide first, form the carbocation, and from below will probably be the major pathway, yeah, and give us the azide at the tertiary position and the alcohol at the secondary position there. And that's under the acidic condition. It's not very acidic. The pK of hydroazidic acid, I think, is 5. It's not too acidic. But these other conditions just don't do that. This is what? Charged nucleophile conditions, neutral here. So the N3 anion would add at the secondary position and pop that open. Remember, charged nucleophiles add less substituted. Acidic conditions, nucleophiles add at the more substituted spot. Conformations here, lowest energy conformations has the biggest groups, staggered and away from each other. And make sure you're using the right molecule here. Some of these are not using 2-methylbutane. These are staggered here with these two methyls anti to each other. These two methyls are gauche to each other. You always have at least one gauche interaction there. But certainly the eclipsed ones are going to be higher in energy. Okay? And this isn't even that molecule. This is the wrong molecule for that. Okay, HBr, yeah, we've been doing that type of thing. Bromohydrin here, the electrophiles, the bromide, and then the alcohol comes in anti to it, the major one, but at the more substituted spot. A and B are close. There's a lot of A that's also formed here, but B is really the key one here. If the bromonium ion is blocking, say the bottom face, the water would come in at the tertiary position from the away face from the bromonium ion. B there, be the correct one. These are the wrong regio chemistry. Anyway, that's a little bit tricky one. That gets into the details of the mechanism a little more. All right, we've been doing ones like this, I think. Here's a 1,2 hydride shift with the tertiary carbocation and the alcohol there. Hydroboration, yeah, so we can just ask you about single type of reactions there. It's always a good thing, to pick the combinations of ones we've covered. We haven't covered oxymercuration. Sometimes this is covered in different books, but don't pick reagent combinations that obviously aren't the ones we've covered. Okay, that's probably showing you're on the wrong path there. Which base cannot deprotonate acetylene? So here the pK of the terminal acetylene, I assume that should say terminal acetylene, is 25? So anything that has a conjugate acid, higher than 25 or lower than 25 is not going to be correct. So yeah, if we have vinyl lithium here, and if you draw that reagent out, it's an alkene with a lithium anion there. That's certainly going to be strong enough. The pK of an alkene hydrogen is 45. So if it's higher, that conjugate acid is higher, that'll be able to do it. Sodium ammonia, amide, sorry. The ammonia proton is pK of 38. It's the ammonium, the protonated form, the cationic form, that's 9, okay? The neutral form is 38. Hydroxide, that would give, 15 for water, so that's lower. So you see hydroxide's not strong enough base to deprotonate acetylene, whereas methyl lithium, 55 there, certainly deprotonated that. So some conditions, so this is what, hydroboration, and it doesn't matter, both sides are equal to the symmetry, and then enol, and then tautomerization to a ketone, okay? Proximity of withdrawing groups stabilize the conjugate base here. That's an inductive effect due to these proximity to the polar covalent fluoride bonds will make the O- more stabilized and lower that pKa to about 2 or 0 pKa, much stronger than acetic acid itself. Here we got a similar thing with epoxides. Yeah, another epoxide reaction. Acidic conditions, so we want to protonate, and then the nucleophile adds anti to it. That would be right here. This stereocenter is the same for the alcohol, so that's still the S stereocenter right there. And then coming in on the opposite sides, the major pathway there. You could say some A is also forming there, but I think C with the attack away from the epoxide would give the major product there. The other two are the wrong regioisomer. Again, yeah. How many isomers upon treatment? Yeah, that's the only one where they're all the same. Slow step, bromination, yeah, endothermic, we just stated that again. Which will be the fastest in methanol now. So the tertiary one, because what? Methanol is a neutral nucleophile, so SN1, correct? So all the others are less substituted. They'll be a lot slower than this one. Different mechanisms, right? SN2, SN1. The rate limiting steps are very different there. So here we have a charged strong base with tertiary. So that's a bad combination, right? This says SN2 or E2. This says what? SN1 or what? E2. So what wins out there? Well, because the backside of TAC is going to be so slowed down due to sterics, grabbing one of these 9 equivalent hydrogens is much more feasible. That gives the E2 elimination product right there. Okay, NMR, different ways we can ask NMR. We're indicating these 2 hydrogens. What's the splitting intermediate? Yep, doublet, just 1 hydrogen there. IR, when we excite a molecule with IR frequency light, we begin to put bond lengths and bond angles, deformations there. So stretching and bending is the basis of IR spectroscopy. I like this problem 36. This is kind of a thought problem here. You've got to really think about this. Hydrogenation gives a compound here. You're told the starting material is chiral, and conversion to the product is also chiral, also optically active. So notice these don't have stereocenters, so they're not chiral to begin with. These are both chiral, but if you hydrogenate here, then you have the 2 ethyls, and that becomes what? Not a stereocenter, whereas when you hydrogenate here, this is still a stereocenter. That will give a chiral product, so D. So it kind of flows through a couple questions there. The only one that's consistent with the correct answer is D. Chiral molecule, these all have symmetry elements. This one does not, though, right? So this would be your chiral molecule. Absorbance at 1600 in the IR. So that's kind of recognizing, yes, there will be a data sheet on the final. There'll be some IR numbers. I don't know if that one's on there, but there'll certainly be the carbonyl frequency, which is what? You've done enough problems with carbonyls to know that they're at, 17 or so. Nitriles triple bonds are up around 22. Alcohols are what? 3,300 in broad due to hydrogen bonding. What's 1,600? Well, if carbonyls are at 1,700, if you have a carbon-carbon double bond, right, that's lighter, a weaker bond. So yeah, that'll be at a lower inverse wave number. So, use your understanding of the few functional groups you know, and usually you can figure out these even if we don't show you those numbers on the data sheet. So don't try to memorize all of them, do enough of the functional groups, and then be able to compare things to what you know. You should be able to rule out all these other ones and get down to that one. NMR1, the only one consistent here with this line list data is right here, due to the doublet way downfield at 5.6, right? So the 2 chlorides make this further downfield. Yeah, I think you can figure out the rest there. Oh, more cyanide stuff. Or no, more epoxide, sorry. Form the epoxide here, and then cyanide attacking from the least hindered spot, and then popping it open, and so they'll be trans to each other there. It'll be a mixture, a racemic mixture, but that's the only one where they're trans with the cyanide at the less substitute spot. Yeah, so B there, if you go through the rest of the mechanism. Chloronium ion, so bromination and chlorination of alkenes goes through the cyclic chloronium ion. And this is actually kind of a resonance structure that if you break that back open, you put that third lone pair on chloride, and that's neutral now, and you have a carbocation. But to avoid the carbocation, the lone pairs on the halogens come over and they can bridge, okay, like that. And you have the positive charge on the halide. So D is the correct answer. This is just another nomenclature thing. Alkene has priority, and then you number through the alkene. Lowest possible numbering, I think, is around here, 1, 2, 3, whatever. You can figure that out. More stereoisomers here, including enantiomers and diastereomers. So that's all the stereoisomers, right? How many stereocenters? 1, 2, 3, 4, 2 to the 4, yep, 16. Same thing here. Here you're asked about this compound, the enantiomer of it. So the enantiomer of this will have what? All the stereocenters inverted, and that's C here. The wedges and dashes help you out there. Okay? And chair, cyclohexanes, the most stable. Make sure you have the 1,3 trans relationship here. And put the isopropyl in what? Equatorial position. And that gives you what? The methyl has to be axial there. Okay? And that is the most stable form. Don't have them both equatorial. This is now not trans anymore. This one's cis. So there, you know, if you're still struggling with that, make sure you have models available you can use on the tests there. Electrophilic addition, we talked about that. We talked about this. Ozone, yeah, we did a harder one for ozone. This is a little simpler problem here. Mechanism here, so we're asking about the secondary bromide with hydroxide. How do you draw the arrows? So you have to know the basics of the key reactions there. And there's what? Our lone pair from our nucleophile attacking, forming the new carbon oxygen bond with loss of bromide anion. So it's A, of course. E2 stands for, so there are definition type questions here. Make sure you know the basics of the key definitions that we have on there. Radiation in the IR, stretching. Single bond rotation, that's microwave spectroscopy. Nuclear spin, that's radio frequency data. Electronic excitation, that's UV absorbance. Okay, light, shining light on a molecule, that exciting things. But IR, there's a couple ways we ask it from. Bond stretch and bend. Okay, stretches are the more important ones. So, reaction here, that's your Lindlar reduction there. 1720. So let's see, cyanide, no, that's 22 or so. Yep, that would be around 17. And don't forget, acids also have a carbonyl. They'll have the OH and the carbonyl. So that's how you can distinguish those two. You'd look up at 3300 and see that one would have that big broad thing there, in addition to something at 17. So yeah, A and B. Some will be combination answers like that. Intermediates here, this is the anti-Markovnikov hydroboration from chapter 15, radical pathway. And there's our addition, right? We'll get the more substituted carbon radical by adding the electrophilic bromine radical on the end carbon. And then we have a polymer question. If we're shown this polymer, what monomer did we have? Well, there's just a methyl here, and then the alternating 1,3 methyl, methyl, methyl. So it must be from propene. The framework here, the carbon chain, always comes from the 2 alkene carbons. And whatever's on the alkene is left over on the alternate position. And yeah, we're almost done. There's 70 on here. Reaction here, multi-step. I think we do the hydration, tosylate, tosyl alcohol, from the leaving group, and then sodium acetates, our charged nucleophile, secondary leaving group. Yep, that'll leave an SN2 there. And here we're doing SN1 reaction with a primary bromide, but this branching, so this 1,2 hydride shift again, and then the water can attack the tertiary spot. General and alkenes treated with borane followed by peroxide. The less substituted alcohols form, the anti-Markov alcohol. What's consistent with this? And here we're just giving you shift data and multiplicity patterns. What's missing here? What can be frustrating is the lack of integration data. So sometimes we just leave it off and we're testing you, we're showing you a bunch of products here, and the only one that's consistent here is this one here, B. This upfield methyl, you see, has just the one neighbor, so that's a doublet. There's another one with just one neighbor here, right? Where's this double here? Well, that's these two methyls right here. Okay. So normally in isopropyl, you know, it's the big methyl's here for the isopropyl, sorry. And then this one here is also this doublet right there. And you got the little one here, which is for the isopropyl, and then this one here is right there, okay, which is a doublet of quartets actually, or a 5-line pattern, a quintet you could call that with the 5 neighbors. So yeah, examine the other 3, you can point out inconsistencies with the data there. This one's a little tricky. In the IR, you're told you're at 1674. Which one here? Well, you got all these carbonyls, right? These would be 17, 17, 17. Why might this one be lower than 17? Well, resonance, right? So you could draw a resonance structure here which would lower the bond order, pushing these electrons out on the oxygen, move the double bond order, carbocation right there, which is benzoic. You can actually draw more resonance structures. All of them lower the bond order here, and what? It goes down to a lower frequency because there's less electrons between that carbon-oxygen bond. And that's common in amides as well. We saw amide resonance coming at lower frequencies in the IR for that carbonyl stretch. Okay, a couple more pages, sorry. LAH, yeah, we've been doing some epoxide reactions. I guarantee you there'll be epoxide reactions on the final. They're a little bit trickier, so maybe that's why they're good to test things, but don't worry, I'm trying to write the final in a simple, direct manner. But I have to cover all the material, so it's good to test you, I think, on some of these harder problems up front, right? So what's the product here? If we brominate, we'll get the tertiary bromide. Eliminate, we'll get an alkene, and then osmium and tetroxide, we'll get the cis-diol. Where's the cis-diol? Right there, A. Sequence here, we're going to deprotonate, put an ethyl group on there, SN2 reaction, Linoir to the cis-alkene. And then this is per acetic acid in place of MCPBA. The way that gives you away is the O3 right there. Draw that structure out. That's a per acid. That will do the epoxidation reaction. And what? The cis-alkene, you see that stereochemistry maintained in C. That cis epoxide is favored. Chlorination here, if you look at these steps, which is not a step in the chlorination process. Here's our initiation step. Here's the propagation step. This is the propagation step. This is not. A hydrogen atom just flying off on its own is not part of that process. So if you examine that and keep the mechanism straight, you see what's not involved there. Mechanism SN1 reaction, yep. Formation of carbocation is the slow step. It's unimolecular. Just depends on the ionization of the carbocation. And terminal alkyne, we did one like that before. Newman projection, go from the Newman projection and try to go back to the hydrocarbons. So it helps to have models here. And you're looking down this front carbon right here, and what do you notice? This must have a tert-butyl group. So, well, all 3 of these have tert-butyls, right? Okay, if that's the tert-butyl group in the front, then what do you have here? You just have a propyl, so there should be an ethyl with 2 hydrogens in the back. But you see an ethyl, a methyl, and a hydrogen. So that can't be it. Here you see that methyl and an ethyl in the back. So it's B looking down this carbon right here at the 2-3 position. Front carbon's the 2, and the back one's the 3 right there. You see the ethyl. More nomenclature. Remember with alcohols, they always have the highest priority, lowest possible number, and that's the 1 position here. Then you got the EZ thing here, this cis double bond, And the IUPAC name is called what? Z at that position. So 2Z. This is E right here for the 4 position. Then you have a methyl and then a 2,4-octadienol, and at the all position, the alcohols at the 1 position. Most heat upon combustion. So we're burning all these things. Which one would give the most heat? Well, it would be the least stable alkene. Which is the least stable overall? It's the less substituted alkene. So this monosubstituted alkene with just 1 carbon on the alkene will give out the most heat because it's the less substituted alkene product. This one with branching will be at a lower set point energy, and around the alkene is 4 carbon group or 3 carbon groups. So that's at a lower point. They'll give out less heat. Same thing here. Disubstituted alkenes will give off less heat too. This one will give out the most heat. Then this one, the cis one, is trans a little more stable than the cis one. That'll give off the next amount of heat, and then the least amount of heat will be there. How many signals in the C13 NMR for the compound below? So this again kind of combines nomenclature. Then you got to think about symmetry. In C13 NMR, we're looking at the carbons. So if you draw out the molecule of methyl cyclohexane, just one more here on the board. Use your scratch paper, right? So how many different non-equivalent carbon sets do we have? Well, the methyl, certainly 1. The methine would be another set. These 2 methylenes, due to the symmetry, would be another set. These 2 methylenes are different than these 2 because they're further away from the methine, so those would be different in the C13 NMR. And then this one at the bottom. So how many total? 5. Okay, different sets in the proton. Yeah, so that's the correct answer there. All right, so very good. We are done with the review. Zoom in. I'll have zooming office hours on Thursday. If you got further questions, you can always email me too, or email Wallace or Austin, and they're still doing their recitations, I think, this week as well. But yeah, if you got any questions, let us know. So very good. You've been a great class, and good luck on the final, and we'll see you soon. Okay, take care. Bye-bye.